So, this is the fifth lecture of module 1 of waves in spacetime and propagation. What we had done so far was to find out what is a infinitesimal Lorentz transformation, and then in terms of this infinitesimal Lorentz transformation, how do you define the change in a particular vector under Lorentz transformation in terms of something which is essentially a matrix defined by capital G. Okay? And these G's what generate or what are called the generators of the Lorentz transformation group. If we look at this tensorial structure and the indices of G, it has Greek indices rho and sigma, and we can consider these to be rho and sigma to be spatial, like in equation 15, 2, 3, 3, 1 and 1, 2, and the same indices to be 1 spatial and 1 temporal, like G10, G20, G30, etc. If we carefully look at this equation, we will see that the mu and nu indices can take values between either, as I have already mentioned, 0 to 3 or 1 to 4. So, each one of the quantities G23, G31 and G12 are essentially are 4 by 4 matrices, and so is the case for one spatial and one temporal component of G, that is G10, 20, 30. We define these matrices by bold M and bold N. It is useful to remember that they are matrices because if we take the product of them in some order and then in a reverse order and then subtract one from the other, that is the usual structure of commutation, then what we generate is what we have denoted by equation number 16. This is the algebraic structure that the capital M's follow. Similarly, the capital N matrices also do follow some algebra, and those are given in equation 17. They are given in two types. One is when the commutation is taken between the n's themselves together, then between m and n, and then between m and m itself. The commutation relation among the m's is something that is closed within itself. That is, their commutation generates elements of m. What usually happens in the case of angular momentum algebra, with epsilon I j k appearing as a Levi-Civita symbol, and the indices I, j and k can take values between 1, 2 and 3, and if the permutation is symmetric between 1, 2, 3, that is cyclic, its value is +1, and if it is not, it is -1. That is what is seen to happen in the case of angular momentum algebra. But on the other hand, if we take a commutation between m and n, let us say m1 and n2, then what we generate as a result is an element of n, which is n3. If we take the same commutation between N1 and M2, what we get is N3. We do not generate a M in by taking this particular commutation relation. What is so special about it? The speciality lies in the fact that if we order our operations in a specific way, first M, then N, and then the reverse, that is first N, then M, and we try to take the difference between the two, we see that they are not same, they are different, and the difference is what is shown as N3. If these capital M's represent the generators of rotation and capital N's represent the generators of boost, then the difference between rotation and boost and rotation is a boost that we are left with. So, for instance, if we take a rotation along the first axis and then a boost along the second axis and reverse their order and take the difference, it turns out to be same or identical as a boost in the third direction. And if these are ordered is 1, 2, 3, then 2, 3, 1, then 3, 1, 2, it is in the same sequence that we produce the boosts coming. That is, first boost in the third direction, then boost in the first direction, and lastly boost in the second direction. Now, what about two successive boosts? So, if we take two successive boosts, one in the first direction, that may be x, then second one in the y direction, and then interchange their order, which is equal to or equivalent to a rotation in the anticlockwise direction about the third axis M3. And this whole thing continues if we keep changing 1 by 2, 2 by 3 or 3 by 1. The next thing that is worth noticing is if we take a operation that corresponds to a rotation in the third direction and followed by the commutation of M1 and N2 and reverse their order, then what we get is essentially a commutation of N3 with M3. Now, commutation relation of N1 and N2 gives me a rotation in the third direction. But if we take a commutation relation between the boost in the third direction and rotation in the third direction, or rotation in the third direction and boost in the third direction, and their difference is actually equal to 0. So, the commutation between the rotations matrices or generators with rotation and boost generators simultaneously does not make much of a difference. The situation remains the same. And similarly, if we decide to take a rotation along the third direction and then take a commutation of N1 and N2, that is boosts in 1 and 2 minus boost between 2 and 1, and it's executed in the reverse order. What we get is no change. So, one can in principle build up these operations one after another in terms of these generators, and one can see that given two different frames of reference, we boost the first one or boost along x direction, then we take a boost along the y direction, or we take the difference between the two, can be represented by a rotation along the third direction. So, whatever variables we have, if we execute these operations of boosting first in one direction and take secondly in the reverse direction, then instead of doing the estimations twice, we can do it once to find out the difference between them by the rotation along the third direction. So, that is a handy outcome that one can use to constrain or check the validity of the expressions or the results that one has obtained. In the next stage, if one goes on to define this infinitesimal parameters of Lorentz transformation matrix by the spatial parts by theta and the temporal parts or spatiotemporal parts as chi, then it is possible to see that the product of epsilon and the matrix G can be written as the matrix M times a parameter theta and matrix N times parameter chi and their addition. So, what does it tell us? It just tells us that under a most general Lorentz transformation or a most general Lorentz transformation can be thought of coming into two parts. One is a boost and the other one is a rotation along different directions. So, what is the outcome of this exercise? The outcome of this exercise is that given a quantity that's if we define it as a phi prime, then phi prime can be thought of the original phi plus boost and rotation of phi about some angle theta and another parameter chi. Okay. So, we'd like to thank you and finish off over here.